All right, this is part two of the digestion and absorption lecture. Yes, it's a lengthy one, but we're going to bring it home, picking it up where we left off with part one, which was at the end of discussing the role of the accessory hormones, accessory organs in the digestive process. And so we're finally now at this place where, yeah, we've been through it all. Let's talk about absorption. How do the nutrients that we've liberated from the food that we've eaten finally get absorbed? And so, again, another great graphic that's been morphed in your newer edition of the Fink textbook that pulls or stretches out your digestive tract and identifies where a majority of the nutrients in the food that we eat get absorbed, right? And so, kind of a nice graphic just to get a big picture overview of where things are going on. Yeah, there's a little note on the side there. About three-quarters of the water that we consume is absorbed in the duodenum, right? And so later in the semester, when we start talking about hydration strategies and the role of water in keeping us hydrated and for performance and all that, we got to make sure that water gets into the intestine to get absorbed, right? Water in the stomach isn't doing us anything, and so it needs to get that far. And then once it gets in the small intestine, we do absorb most of it there. So obviously, the remainder is sort of absorbed later on in the small intestine and also in the colon. So, all right. So let's talk about the cellular at the cellular level absorption of our macronutrients. So carbohydrates, proteins, and fats. And so when we look at carbohydrates in foods, they can be broken down into three molecules: either glucose, fructose, or galactose. Those are the three monosaccharides. I know we haven't talked about them yet in class, but the digestive process takes any carbohydrate, whether it came from an apple, some milk, or a potato, whatever it was, it'll break it down into its smallest components, which is one of those three molecules. Proteins will get broken down. There's 20 amino acids that make up any of the proteins possible, and not all 20 are involved in all proteins in our food. There's some that only have a couple amino acids. There's some that have thousands of amino acids in them in various orders, but there's 20 potential amino acids that can be liberated from the food that we eat. And so those individual molecules, right, they went through the process, from our mouth, esophagus, stomach, small intestine, they finally get broken down into those monosaccharides or into those amino acids. How do they get absorbed across the membrane of the small intestine? And so the two little graphics that we have on the slide here is the membrane of the small intestine. Remember those little microvilli? This is where the absorptive magic occurs. And so carbohydrates and proteins, so again, monosaccharides and the amino acids, are absorbed through two different types of mechanisms. One of them is called facilitated diffusion, and that's the graphic in the middle of the screen. Fructose is absorbed through that process called facilitated diffusion. Facilitated diffusion has a couple of characteristics. First, facilitated diffusion requires a higher concentration on one side of the membrane to force diffusion across to the side of the membrane where there's a lower concentration. So a concentration gradient is necessary. So it won't go from a low concentration of fructose to an area of high. It always goes from an area of high concentration to a low concentration. And the goal is to reach an equilibrium, right? So once the concentrations are even on either side of the membrane, diffusion will not occur anymore. So consume a food high in soda, which you should never do, of course, right? Consume a meal, sorry. Consume a soda. Lots of fructose in that. High fructose corn syrup is usually the first ingredient or so. Lots of fructose in our small intestine. That will cause that high concentration gradient on one side. How do we get it across the membrane? Well, the process of facilitated diffusion occurs. And facilitated diffusion requires what's called a transmembrane protein carrier. And so there's these channels through which the fructose gets transported, and we have these protein carriers that are responsible for bringing it across. What's challenging about facilitated diffusion is that it can get overwhelmed. In other words, if there's too much fructose on the small intestine side of the equation, it will overwhelm the absorptive mechanism, the diffusion mechanism of facilitated diffusion, and some fructose then won't get transported across the membrane. It won't diffuse across the membrane. So it can get overwhelmed. It does not require energy, which is important, but it does require those transmembrane protein carriers. There are a handful of amino acids that get absorbed in this way as well. Um, as an example, if an individual consumes too much fructose in a sitting, and this probably has happened to some of you listening to this lecture, usually in the neighborhood of 30 grams of fructose or more. So we're talking big gulp size soda kind of thing. A huge load of fructose will overwhelm that mechanism, the facilitated diffusion. The fructose will stay in the small intestine, make it to the large intestine. When fructose makes it to the large intestine, the bacteria down there absolutely have a massive party. They love sugar of any form, fructose, glucose, galactose, whatever it is. And the bacteria will ferment that fructose, and the byproduct of that fermentation is gas. So if you've ever had a massive load of sugar, through various forms, but soda, again, is an easy one to pick off, and you get gassy afterwards, that's usually one of the reasons, right? And we can usually tolerate about 30 grams of fructose in one sitting. Depends. The other diffusion or absorptive mechanism for the other two monosaccharides, glucose and galactose, is called active transport. There's also a lot of amino acids that use this as well. Active transport is a graphic on the bottom right of the screen. Active transport does not require concentration gradient. So we can go from a low concentration of glucose in the intestine, and the glucose will still get pumped across that membrane, that cell of the microvilli, which is really important. Getting back to us as organisms trying to maximize the nutrition that we get from the food we eat, active transport is awesome because it's literally a pump. And almost, I was about to say electric pump, it kind of is an electric pump. Facilitated diffusion kind of fails us, but in nature, there aren't too many situations where facilitated diffusion would get overwhelmed because there aren't that many situations in nature where there's that much fructose. I mean, very rarely. So getting back to active transport doesn't require concentration gradient. What it does require, though, is energy. And so there are these channels that will pump glucose and galactose across the membrane, but these pumps do require energy in the form of ATP. So it costs us, it's a little bit of an investment energy-wise for these pumps to operate, but what they do is they ensure that all this high energy sugar basically makes it across the membrane into our bloodstream and can get delivered to where it's needed for metabolism or other purposes. So again, other amino acids, there are several that use this mechanism as well. It's very hard, if not impossible, to overwhelm it. So we can maximize and guarantee we get all that sugar in the form of glucose and galactose into our body. So that's carbohydrates and proteins. Fats use a different mechanism. Fats use what's called passive diffusion. And so passive diffusion is unique in comparison to the other two, as you'd expect. Passive diffusion does require a concentration gradient. I know it doesn't say that on this graphic. When I cut it off of the slide that I had before, I eliminated that, but it requires a concentration gradient. So yes, we need a higher concentration of fat on the intestinal side for it to get transported or diffused across to the other side of the membrane. So there is no specific protein carrier needed, nor is there ATP needed for this. So it's literally strictly a concentration gradient type of mechanism. If there's a lot of fat in the intestine, it will diffuse across the membrane until we reach a point of equilibrium. This is an effective method to get fat across. It's better than facilitated diffusion. Facilitated diffusion, like I mentioned, can get overwhelmed. This is not so easily overwhelmed. So by design, we don't, as humans, with very little fat, should go unabsorbed or undiffused. In other words, fat should not be making it into the colon, and if it does, that's a warning sign. That's definitely a red flag. The term steatorrhea is the fancy word for fat in your poop, meaning that you have a bowel movement and there's fat in it. Conditions like Crohn's disease, which is an autoimmune condition, things like cystic fibrosis are conditions that would lead to a greater likelihood of fat making it into your stool. So, it's not something that we should ever expect. There are some different types of fats, and so this is basically triglycerides. If we look at things like medium-chain triglycerides and glycerol, two different categories of fats. We'll talk about them in a fat discussion much more thoroughly. They use this mechanism, and they enter straight into the bloodstream. So those of you who are into the coconut oil right now or the MCT oils with your bulletproof lifestyles or whatever you're doing, those go straight into our blood. The long-chain fatty acids, the long-chain triglycerides, right, which are typically what we see in most food products that we consume, they first enter our lymph system as chylomicrons and then ultimately enter our blood through what's called the thoracic duct. So don't worry too much about those details. Just from this slide, take that fat absorption uses passive diffusion. All right. So now that we've absorbed these macronutrients, what next? So ultimately, carbohydrates will all be converted to glucose. So glucose, yep, that's our very favorite one. Our brain loves it. Our muscles love it. Metabolism generally loves it. You know all about glycolysis. We'll talk more about it in the next lecture. But the galactose and fructose will be ultimately converted into glucose, so therefore we can use them through those metabolic processes or other ways. When we consume carbohydrates, we do have what's called an insulin response. So the pancreas responds to high amounts of blood glucose, and that insulin response helps get glucose into the cells. Liver or muscle are the two primary cells where glucose can enter. It may be converted to fat or maybe used as energy depending on the situation of the individual at that point. Proteins are broken down into amino acids ultimately, right? We've talked about this briefly. Amino acids will add to what are called amino acid pools in our body. I'll talk about those on the next slide a little bit. Generally speaking, and again, we have a whole unit or a whole chapter dedicated to proteins. They go to things like tissue repair, tissue growth, the formation of hormones and enzymes, hydration status or fluid balance, electrolyte status, or sorry, not electrolyte status, hormone formation, lots and lots of functions of protein. So depending on what your needs are, the proteins will go there, or they'll go into one of the dedicated amino acid pools, which we'll talk about next. Fats, which are ultimately broken down into triglycerides in our small intestine, they get, again, we mentioned on the previous slide, they enter the bloodstream as part of what's called the chylomicron, or if they're coming from the liver, which isn't through the digestive process specifically, but they enter the bloodstream as a VLDL, very low density lipoprotein. They'll float around. They'll either enter a muscle cell to be stored there or to be used for metabolism, or they'll enter a fat cell and be stored there. So different fates of all three of our macronutrients. And all, again, are depending on the status of the individual and what they're doing at that point and what their needs are. So I want to spend a second talking about the amino acid pool. We'll touch upon it in a little bit more detail in the protein talk, but it's worth mentioning here. Our body has what are considered two primary sites of amino acid storage. There's more, but there isn't, the more are such small storage sites that these two main sites are at least the tangible amino acid storage sites where it's like, yeah, there's a lot of amino acids there that we can use. So the first of these pools is in our tissues, especially muscle, right? And so muscle and liver combined are the greatest source of our amino acid storage, and that's the biggest pool. If I were to ask you on an exam, it'd be the combination of these two, or if there's just one choice, choose muscle. Muscle on an individual, even if you're a skinny individual with not very big muscles, muscles will be the largest site of amino acid storage. Liver will be second place. So if the option to combine the two on a multiple choice question is there, combine the two. The second amino acid pool is called the free amino acid pool. And the free pool is a pretty cool thing, right? And so one thing with our body, and we'll touch on it in the metabolism discussion coming up, but amino acids and kind of everything, but especially amino acids, are constantly being used for things and needed in one place. And so there's this exchange of amino acids needing to go to one place, and we free some amino acids up to help build tissue here. And so there's this constant exchange and this constant fluid, almost movement of amino acids. Well, it'd be really tough if we had to go to our main storage site of amino acids, which is the muscles, to liberate proteins, amino acids, to form some enzymes. That'd be really tough because you're working hard as an athlete potentially to gain muscle size. And then all of a sudden your body's like, you know what? We need amino acids to make this enzyme to break down whatever carbohydrates that you just ate. We would lose muscle protein in that process. It happens, but it'd be great to minimize it. And so the idea of this free amino acid pool accomplishes that. It is a source of amino acids that are unattached. In other words, they don't serve a specific function and are ready to jump into action wherever they are needed to prevent us having to tap into our other amino acid pools, which are the muscles and the liver. So the most abundant amino acid in that free amino acid pool is glutamine. Some of you may supplement glutamine as a recovery amino acid. It is for that reason. If we replenish that free amino acid pool, that glutamine will go help to repair muscles that you just used for a workout versus amino acids coming from a different muscle to repair a muscle that you just used, which can happen. So the size of the two pools are massively different. And if we look at an average individual, 155 pounder-ish, body protein may be about 10 kg all overall, so about 22 pounds. And that's just from the muscles, that's muscle mass. The free amino acid pool is about 100 grams. So we're looking literally at like 100th of the size of in comparison. The free amino acid pool is about 100th the size of the amino acids we have stored in our muscles. So it's very, very small. During a longer exercise session, we could burn through metabolically that 100 grams of the free amino acid pool, no problem. So it poses some interesting challenges when it comes to exercise and protein status. We'll get to those later. All right, moving forward. This next set of slides is always an awkward one to me because I don't ever know exactly where to put it. So I've let it sit here in this digestion metabolism zone because the next talk is metabolism, and I think it has an okay home here, but it'll come up throughout the semester. Fat synthesis and storage. And so, through this whole process of digestion and absorption, we talk about the storage of fat and, do carbohydrates get stored as fat and what happens to fat and all this kind of stuff. So we have this discussion here to kind of cut to the chase and discuss these things. So firstly, the chylomicrons. You should remember the term chylomicrons. Chylomicrons from the intestine. Chylomicrons are literally like a taxi cab for triglycerides. So triglycerides are that simplest component of a fat molecule. It's a glycerol, so a 3-carbon molecule, which is glycerol, with these free fatty acids hanging off of it. We'll talk about those in great detail in the fat talk. Chylomicrons, and then very low density lipoproteins, which come from the liver. That's usually from the conversion of carbohydrates to fat in the liver. And then the liver dumps those fats in the form of very low density lipoproteins into the bloodstream. Those are our two fat carriers, our two triglyceride carriers. Once we have fat in the cells, it has a couple of fates. First, it can go to adipose tissue. It can go to fat tissue. There's an enzyme that is at the wall of fat cells called lipoprotein lipase. Lipoprotein lipase will break down a triglyceride into a monoglyceride, which is basically a glycerol molecule with one fatty acid hanging off of it, and then leave those other two free fatty acids floating around. It'll break up that triglyceride molecule to allow the triglyceride to enter the cell. Triglyceride by itself is too big to enter a cell, so it needs to be broken down. So lipoprotein lipase allows a broken down triglyceride to enter a fat cell, and then once it's there, the magic of the magic of our body basically reforms. It's not that magical actually. It reforms that triglyceride, and so we break a fat down to let it enter the cell. Once it enters the cell, it reforms, and that's how we ultimately store fat. And again, there's a lot of details missing there, but at least conceptually, fat in the bloodstream gets delivered to a fat cell. Lipoprotein lipase breaks the fat down to allow it to enter the cell, and then it reforms once it's in the cell. The question about carbohydrate storage to fat, and this comes up a lot, right? A lot of people say, if you eat too many carbs, they just get converted to fat, and you're going to get fat from eating carbs. There's some truth to that, but it's not entirely that simple. High carbohydrate consumption, overconsumption of anything, ultimately, beyond our body's energy storage needs or capacity will lead to increased fat storage. Our body can store protein as fat. Obviously, our body can store fat as fat. And it can store carbohydrates as fat. So, but let's talk a little bit about what happens in this process and why firstly, how carbs can be stored as fat, and then secondly, why eating a lot of carbs can ultimately lead to fat gain. So in our liver and in our fat cells, we have the process of glycolysis that occurs. And so I'm going to take a pause here in our discussion. Apologies. All right, I'm back. Apologies for that. Let's get this back up to where it needs to be. Okay, so we're talking about carbs and carbs being stored as fat. So if we're consuming too many carbohydrates specifically, right, how do they ultimately get converted to fat? So in the liver and in fat cells, carbohydrates will enter and they go through that process of glycolysis. And again, I know you guys have had the prereq of physiology for this class, so you know what glycolysis is. The next lecture covers glycolysis in great detail, so you'll know all about it. Through glycolysis, the carbohydrate, let's say we get into the fat cell, or in the liver cell, doesn't matter. You pick your cell. The glucose will get broken down through the process of glycolysis and end up being a pyruvate molecule, and that happens in the cytosol of the cell. The pyruvate will enter the mitochondria and get converted to acetyl-CoA. And hopefully you're all familiar with that process now. Like I've already mentioned a couple times, in the next lecture, you will be very familiarized with it, but hopefully you already have that. That's the purpose of your prereqs. So we have glycolysis and then the conversion of pyruvate to acetyl-CoA happening from this excess carbohydrates that we're consuming, right? If we're exercising and carbohydrates enter our body, the carbohydrates are going to probably go to our muscle and our muscle's probably going to use them to generate ATP. If we're not exercising, then yeah, where do the carbs go? Well, we have that insulin response and the carbohydrates will enter the liver, they'll enter the fat cells, they'll enter our muscle cells as well. And so once they get in there, glycolysis happens. Glycolysis ends up giving us pyruvate. Pyruvate then gets converted to acetyl-CoA. Once we start making this acetyl-CoA, and again, the reason that we have the acetyl-CoA and all this happening is because we're not exercising. Acetyl-CoA shouldn't be building up, but if we're eating too many carbs, we had that big gulp of Coke, the acetyl-CoA starts to accumulate. And so we start to get this accumulation of acetyl-CoA. The body doesn't have anything specific to do with it. Normally it'd enter the Krebs cycle and we get all this wonderful ATP ultimately from that, from the electron transport chain. But if we don't need the acetyl-CoA for energy, the acetyl-CoA start to accumulate. And so first, we can have the formation of two acetyl-CoAs joined together, and they form something called acetyl-CoA, which is actually a keto acid. So some of you into ketosis and ketone bodies, that's a ketone body. But if we have too many acetyl-CoAs being formed, and especially from the breakdown of carbohydrates, from the breakdown of glucose and glycogen, the acetyl-CoA, the length of the molecules will keep growing. And so there's a enzyme called fatty acid synthase that actually joins acetyl-CoAs together. And so what we get is a long chain of acetyl-CoAs. And if you're into the whole chemical structure of acetyl-CoA, acetyl-CoAs are two carbon molecules. And so we have these chains of carbons building ultimately to get to be in the neighborhood of about 16 carbons long, which is the equivalent of a fatty acid. And so, again, too much carbohydrate consumption, carbs enter the cell, they go through glycolysis, they form acetyl-CoA, acetyl-CoA start to form together. Intermittently, they make a little keto acid, but then there's too many acetyl-CoA, so we add more and more acetyl-CoAs to the chain. Now, all of a sudden, we're starting to form fatty acids. Once we have 3 fatty acids formed, they can quite easily find a free glycerol molecule to attach to. And if you add 3 fatty acids to a glycerol molecule, you'll end up with a triglyceride. Again, kind of wordy, kind of out there, and hopefully you followed along with the process. Think does not get into it, so know the basics of these slides that I'm talking about right now before I move on to the next one. So ultimately, yes, glycolysis precedes the formation of fat. So glucose goes through glycolysis before it ultimately becomes fat. We're going to keep going along this. Here's a little bit of a graphic. I don't think it's that helpful anymore, so I'm not going to keep it up here very long. You can pause the lecture if you want to have a look at it. It does get into this process a little bit with this increased consumption of glucose, ultimately going through glycolysis and forming acetyl-CoA. You can follow it along. Don't worry about it. I'm not going to test you on anything from this graphic specifically. So let's continue on with this carb storage to fat thing. So now you're thinking, well, yeah, that makes sense. So if I eat too many carbs, this whole process will occur and my body's going to store tons of fat from carbohydrates. Well, not so fast. This whole fatty acid synthesis process requires a lot of energy. Our body does not like to do it. It is the best description is it's very inefficient. And so we need ATP through this process. I didn't identify where and how, but ATP is used to convert the acetyl-CoA to the free fatty acid. To get those acetyl-CoAs joined together and all that process, we need to throw some ATP in there. And so to form one free fatty acid of palmitic acid, and so palmitic acid is a 16 carbon fatty acid, so 16 carbon chain. That's the length of fatty acid that our body loves to make. It doesn't like to make longer ones or shorter ones. For some reason, the 16 carbon length is what our body loves. So that 8 acetyl-CoA, right, 16 divided by 2, requires 7 ATP and 14 NADHs, which, as you know from the Krebs cycle, they're typically formed in the Krebs cycle, 3 ATP per NADH in the electron transport chain from that. That is a boatload of potential energy it takes just to make one fatty acid. So it's like, wow. Ultimately, when we break down fats, we do get a lot of ATP back, but that's a high investment for pretty low yield in relative terms. So, so this efficiency factor, it's about a 12-to-1 ratio-ish of carbohydrates to triglyceride conversion, meaning it takes about a unit of 12 carbohydrates to form a similar unit of triglycerides. Not a good ratio for our body. Our bodies like to try and be as efficient as possible. So, and this is just sort of building off of that discussion. So the conversion of carbs into fat is about 10 times less efficient than simply storing fat in a fat cell. So in other words, if you had a meal of carbohydrates and needed to store them as fat, the body's a lot less likely to store those excess carbohydrates as fat as it is likely to store fat as fat. Right? And I'm going to say things later in the semester that are going to sound like the exact opposite. It's not, but it will sound that way. So the conversion of carbs into fat is about 10 times less efficient than simply storing fat as fat. So here's the example. If you have 100 extra calories in fat, about 11 grams, floating in your bloodstream, fat cells can store it using only about 2.5 calories of energy. It's easy to get fat into fat cells. It just is. Kind of makes sense. If you have 100 extra calories in glucose, about 25 grams, floating in your bloodstream, it'll take about 23 calories of energy to convert that into fat and then store it. Our bodies are smart. Our bodies don't want to waste energy to store the carbs as fat. They'll just store fat as fat. So ultimately then, what's the deal? Why are we thinking and why are we discussing eating too many carbs makes us fat? Specifically and technically, they don't. And so we'll build off of that, and there's going to be some nuances there. That's what I love about this field is that there are so many things to discuss and so many little factors. So carbs don't make you fat via direct conversion and storage to fat. And so in other words, yeah, eating a lot of carbs can lead to fat gain, just like eating too much of anything. But too many carbs, as we now know, it's an expensive process to convert them into fat. So what happens and why too many carbs can lead to increased fat gain so easily is because, well, there are a couple factors. First, when we eat too many carbs, it will slow down or stop fat breakdown. And so excess carbohydrates if there's carbohydrates available, your body's going to use them. And if your body's using carbohydrates as an energy source, fat breakdown is going to stop. So guess what? We got plenty of carbs coming in. Turn off that motor or that furnace over there burning the fat. We don't need any more. The carbs are so much easier to break down than the fats. So when we eat carbs then and we consume fat with the carbs, which happens quite often, look at a French fry, right? That's the perfect combination of, oh my God, crappy carbohydrates and crappy fat. Hey, the carbs are going to stop fat breakdown and the rest of the fat in that French fry is going right where you think it's going to go. So the excess carbs will stop or slow down fat metabolism, fat breakdown, and therefore the fat that you consume is much more likely to be stored as fat. So yeah, a 500 calorie surplus of fat and a 500 calorie surplus of carbs can both make you fat. The carbohydrate consumption will also lead to an increase in the release of a hormone called insulin. And insulin is in part responsible for that decrease in fat oxidation. If insulin is in the blood, if it's being released by the pancreas, insulin will stop fat oxidation and basically make it so that we're using ultimately carbohydrates as an energy source primarily. So some of this information comes from the website bodyrecomposition.com by Lyle McDonald. He's an interesting character, definitely worth a visit if you are looking for more information and more depth from that conversation. So have at it. All right, let's move along. We're almost done. So we haven't talked much about vitamins, minerals, and water, their absorption, whatever, what happens to them. And so we're not going to spend much time actually talking about them in general. Here are the important things. So vitamins and minerals are contained in foods, right? They're naturally a part of the different foods we eat, vegetables, fruits, meats, dairy. They all have their different complements of these micronutrients, right? These micronutrients are not food products per se. They're not a macronutrient. They're not a carb, fat, protein. They're not fiber. They're none of those things. And so they have a unique sort of standing. The body themselves, the body wouldn't recognize them, right? And so when you take a vitamin, like if you take a multivitamin, why does it usually say you should take it with food? Because if you put a multivitamin in your stomach, your body's like, there's nothing in here that's going to trigger digestion, because it's almost as if you just ate a grain of sand or something like that. Well, there's nothing there to digest it. So the digestive process releases these vitamins and minerals from the food that they're contained in, and they do so in a way that also enables them to be absorbed into our body. And again, absorption happens in the small intestine is primarily. Large intestine, again, is for mostly electrolytes and water and vitamin K. So again, they get absorbed through similar mechanisms. Sometimes it's quite often just passive diffusion, but there are other mechanisms in play with them. As we discussed earlier, most water is absorbed in the small intestine, but there is some reserved for the large intestine as well. Think, and even the dark side, talk about something called motility and transit time. And so these are terms that describe how long it takes for food you eat to make it from point A to point Z, right? So from intake to elimination. So food spends in the neighborhood of 1 to 3 days in your GI tract. That's what we talk about when we use the term transit time. Transit time, how long is the food in your body? I just ate an apple. How long is the skin, which is pretty much the only thing that remains intact, going to leave my body? You can time it. So the ideal transit time is in the neighborhood of 16 to 24 hours. I think Sean on the dark side has a little bit different numbers on transit time. If I ask you on an exam, I'll try and make it clear. I won't be like, 18 to 20 hours, 20 to 22 hours. You should be going once a day, like for sure. Twice a day, researchers, doctors, medical professionals that are into digestion usually say, yeah, ideally you're having 2 bowel movements a day. You go poop twice a day. 3 is getting borderline too much, and transit time's not long enough. But if you go less than once a day, that's also not enough. So again, more than 24 hours between bowel movements is too long. We don't want stuff to stay in our body. We don't. So the average American transit time is ridiculous. It's horrible. 72 hours is painfully long. And there's no pun intended there. It is painful and it is long. So, if we look at the different components of our digestive tract, stomach, depending on what we ate. Small intestine, that's about that many hours. Large intestine, depending on, again, what's in it, 12 to 24 hours. Could be a long time. What things affect our bodies, what things affect this transit time? Well, there's a lot, right? Firstly, the food that you're eating. If you're eating a plant-based diet, plant-based products make it through our body much more quickly. Typically, foods that are high, especially in dense proteins, things like meat, are much slower to digest. They spend a lot more time, especially in the stomach. Small intestine and large intestine, it's hard to slow them or slow them down much. You can speed them up a bit. But people on a more meat-based diet and low fiber diets, they're going to have a longer transit time compared to people who eat less concentrated protein sources and eat more fiber. There's also gastric emptying, which is part of this equation, which I've already kind of alluded to. Things that'll slow down the rate at which products leave our stomach, foods high in protein and fat, will take longer to leave compared to foods high in carbohydrates. Mentioned that already. Particle size. If you're not doing your 25 chews per food and you just swallow a piece of meat without chewing it, that piece of meat could be in your stomach overnight. There's no doubt. It's going to take a long time to break that down into chyme. So the particle size, so how well you chew, will have an effect. Things like osmolality, which we'll talk about in the fluid discussion and the hydration discussion, but the thicker the product is, so to speak, right? So if you're drinking like maple syrup, which has a really high osmolality, that's going to stay in your stomach longer than water, which has an osmolality of 0. Osmolality is a factor associated with how concentrated fluid is. Energy content, so the more energy content in a food, so the more energy dense it is, the longer it'll stay in the stomach. Carbohydrate content will slow things down, but not as much as protein and fat. Exercise. If you're exercising too hard, there's no such thing, right? If you're exercising at higher intensities, blood flow gets directed away from the GI tract, and therefore digestion will slow down. And so, speeding up gastric emptying, well, the more your stomach is stretched, the greater pressure that puts on the pyloric sphincter, and the more likely foods are to leave it. And so, and then obviously the opposite of the things that'll slow it down. So, digestion and exercise, also worth talking about for a slide. There is a high incidence of gastrointestinal issues with exercise. It depends. All of you who are watching this probably have different thresholds, right? I know some people who can eat a burrito and go for a hard run, where I know some people who can't eat within 3 or 4 hours of going for a run, or they're going to get cramps and stomach ache and all that kind of stuff. So there's definitely a spectrum of individuals and their tolerance. So the incidents, the most common ones, cramps, and that's more side aches, stomach ache kind of cramps, right? Not like a calf cramp. Diarrhea, quite often. The urge to go, so not like you are going, but you just feel like you need to go. Gassiness, also quite common. Less common gets into a little bit more extreme sort of side effects, vomiting, bloating, heartburn. The side ache is on there as well, but side ache and cramps are kind of the same to me. Some of the causes, right? And there's multiple causes. First, when we're exercising, blood flow to the GI tract decreases, which means the organs associated with the GI tract slow down the digestive process. So food has a longer time to sort of sit and cause issues, right? A stomach full of food, that food is going to sit in your stomach longer, and that can cause discomfort. Nervous system. Some people also get nervous before they exercise. I counsel some athletes that, before every match, I have to go diarrhea. I'm like, well, that could be a problem. But it's like, well, it's every match. Okay, well, then let's expect it to happen. Why is this happening? Is it food-based? No, it's just nerves. And so our nervous system, right, it still communicates with the ETS, right? And so we can see that when people get nervous, they're more likely to eliminate. And so if we then can be practical and go, okay, make sure you do some extra hydration, a little extra energy before, deal with it. But the nervous system can cause a lot of those issues. There are mechanical issues. So depending on what you're doing for exercise, your posture could be conducive to issues not allowing food to make its way through. Like, if you're not fit well on a bike, right, and you're crunched over too much, you could be even putting pressure on the stomach or on the intestines to not allow food or food products to make their way through. And then just the nutritional content of the food that an individual eats, right? If you do have that big old, carne asada burrito before you exercise, no wonder you're going to get cramping and nauseated. That stomach's going to be sitting in your food. Your body doesn't like that. So and things like dehydration and other habits or other situations can also cause some of these issues with exercising. Prevention, so there's some good strategies of preventing these issues. Dairy products tend to be a more common offender when it comes to these GI issues. So a lot of times, even if you're not dairy sensitive or lactose intolerant, just drop the dairy before you exercise. Give it a few hours. High fiber foods, because they move through quickly, they would like to leave quickly, and they can sometimes, especially for more endurance athlete types, can cause some issues during longer exercise efforts. Non-steroidal anti-inflammatories, NSAIDs, they cause issues with what's something called leaky gut, right? They affect the permeability of the lining of your gut, meaning that they could lead to things getting through the lining of both your stomach and your intestine that shouldn't, and that can lead to issues and stomach discomfort the things like ibuprofen and that kind of stuff. They can lead to just gastric upset by themselves, but the leaky gut issues are sort of a compounding factor. Products high in fructose, we mentioned how fructose can make it to the colon and have a bacteria party and make you gassy, no good. Avoid dehydration. That's just for multiple reasons a good idea, but also for digestive health. Over-consuming food, so going in with the full stomach, really can make things complicated. Most people figure that out by the time they're in high school, but sometimes it takes some trial and error. And then drinks that are hyperosmolar, so drinking drinks that are too concentrated with carbohydrates and proteins or whatever else is in those drinks, the body needs to dilute them before it leaves the stomach, and that can be quite stressful and cause GI issues as well. So there's some strategies. All right, a couple more slides. Bugs. Bugs are so worth talking about. They're worth really a whole class, not just a couple slides within a class, but our gut, so stomach through colon, has trillions of microorganisms. There's approximately 10 times more cells, more bacterial cells in our gut than there are cells comprising the human body. So if you think about that for a second, there's 10 times more bacterial cells in our body than there are human cells. So you are 10 times more bacteria than you are human. Let that settle for a minute. These bacteria are incredible, right? And so they have a whole range of complexity in terms of their function and structure, actually. At least 600 species have been identified, and that number is growing constantly, which means it isn't just a couple, right? And you'll often see probiotic types of foods, yogurt, saying, oh, there's lactobacillus. There's a couple really common ones, but there's hundreds of different types. And so most are yet to be discovered. About a third of them are growable, which means clinicians, doctors, people in labs are able to grow them. Some just aren't growable. They just exist in your body, and if they take them out, they die. Function is poorly understood, I'd say yes right now, but the picture is getting better. And the picture associated with the health and the balance of the bacteria in our body and how we function as humans, the more we learn about them, the more exciting and mind-blowingly important they are. It's just incredible. So generally, these bacteria in our body are stable. Like, there is a balance that exists within our body that helps keep us healthy. They help with digestion. They help with mental health. They help with so many things. And if they're in balance, things are good. But they can be messed up. And in our society, in our world, the balance of bacteria in our body can be messed up or perturbed pretty easily, right? Antibiotics are probably the main offender, right? So if you go on a cycle of antibiotics, you are guaranteeing that you're going to mess up the balance of flora of bugs in your body. Certain medications, having an infection, people who are constantly stressed out or exposed to certain types of toxins, even poor diet can affect it. But generally, again, it takes a bit to push them out of balance. But when they're out of balance, we really need to fix that, because we can suffer some serious GI issues if they're out of balance. So ways to ensure that we have balance. Well, there's foods that contain these live bacterial culture. We call them probiotics. Things like yogurt, sauerkraut, kimchi, kombucha, which has become incredibly popular lately. Those are all foods that contain natural, good bacteria that when we consume them, and they're usually resistant to the acidic nature and the acidic environment of our stomach, they will make it into our intestines and our colon, and they will grow and thrive and play out the roles that they play. The term prebiotics is something you may come across, and these are food ingredients that promote bacterial growth. And so the prebiotics are what feed the probiotics. So the bacteria, when it makes it into our body, they need food to grow and to multiply. They really like carbohydrates. And so most prebiotics are some sort of complex carbohydrate. Soluble fiber and resistant starches are the two main types of foods, or at least components of foods, that contain prebiotics. And we'll talk about those more in the carbohydrate discussion. So disruption of this flora will cause gastric issues. And again, the functions of the flora we'll talk about on the next slide. But the gastric issues can range from leaky gut, which is, again, as mentioned previously with the non-steroidal anti-inflammatories. Particles make it into our body that shouldn't. Sean talks about this in chapter 8 quite a bit. And actually, Sean talks about what happens when the gut flora gets disrupted much more than I do. Be familiar with these factors. But the bacteria make up a major component of our immune system, so we are more likely to get sick. We are more likely to have things like diarrhea because of incomplete absorption or breakdown of foods. And so there's a whole sort of massive menu of things that can happen when our gut flora gets disrupted. And so how do we take care of it? How do we maintain it? Well, for some people, making sure that they eat a complement of probiotic foods on a semi-regular basis, right? It doesn't have to be dairy-based. It can be things like sauerkraut and other fermented foods. Minimizing stress, minimizing exposure to toxins, staying away from antibiotics and other drugs that might disrupt function of bacteria. Those are all good things. some of the functions of this good bacteria in our body. And this list is continuously growing, and I should have updated even since the last time I did this lecture. There's been new discoveries. But first and foremost, production of vitamin K and biotin. So they're producing some vitamins for our body. These are essential vitamins that we need for life. We can get them through food, but man, if a bacteria is making them, that's all the better. They destroy harmful bacteria, and that's part of their immune system function, or one of them. They ferment unused nutrients, so when carbohydrates and even some proteins make it into our colon, they'll break them down. They reduce gut permeability. That's that leaky gut stuff that Sean talks about in Chapter 8 in the dark side. That's a good thing. We don't want leaky gut. We really, really don't. They transform and promote excretion of toxic substances. So they help us eliminate basically the bad guys in our body. They enhance fecal bulk. And so about 2/3-ish, half to 2/3 of the bulk of our stool, of our poop, is dead bacteria. I mean, we have in the neighborhood of 2 to 4 pounds of bacteria in our body at any given time, right? And that bacteria doesn't always have a very long life. So there's constantly new bacteria being formed while old ones die. Well, the old ones dying become part of our fecal bulk, which isn't a bad thing. We need fecal bulk. It keeps our digestive tract healthy to push that through. So, they stimulate immune function. Some of the newer stuff, they're talking about brain function and mood. Serotonin, about 95% of serotonin, which is that happy hormone, is made by bacteria. And Sean, again, talks about that. So I'll keep alluding to Sean's role in this part of the discussion. So lots of really important reasons to take care of the bugs in your body. All right, so my favorite part for face-to-face discussions, and the really awkward part about an online discussion, it's time to talk about poop. Poop is a big deal. We need to understand, we don't have many ways to see how our digestive tract is doing, right? How do we gauge how well we're digesting and absorbing food? Well, this is it. Look at your poop, because otherwise there's really, unless you're having like severe issues, gassiness, cramping, bloating, right? You could be symptom free, but if there's something going on with your poop, that's a better sign of, there's something going on. So let's cover some of these bullets. So in terms of frequency, how often should we be going? Already mentioned this. We should be going at least once a day. Twice a day is sort of the sweet spot. 3 times is on the borderline of too often, but less than once a day is on the borderline of not enough. So once a day is optimal. Consistency. What should it feel like, right? I'm not suggesting you touch it. But the consistency, and if we look at the Bristol stool chart on the right side of the screen here, a type 4 poop is the optimal one. So like a sausage or snake, smooth and soft. Some people liken it to a banana, maybe not an overly ripe banana, but a banana. So that is the consistency we're after. And if you look at the Bristol stool chart, which is a chart used in the medical field, so this isn't something I made up, you deviate from 4 and you get up to the type 1. We're talking really, really dehydrated, almost like a rabbit poop. Very little moisture, typically very little fiber in the diet. So dehydrated and not eating fibrous foods. Where you get on type 7, where we're talking, man, there's almost nothing to it. It's literally close to diarrhea. Maybe overhydrated, maybe too much fiber, or maybe lack of absorption of foods and lack of breakdown of foods. And so things get passed through quite quickly when that happens. So again, multiple causes to deviate from a type 4, and the farther away from type 4 that you are, the more reason for concern there should be if it's not a regular thing. So color, what color should it be? Well, that depends. It depends on a lot of things. Color is typically associated with the food that you eat. And so if the color changes dramatically, but the food that you ate didn't, that's a red flag. If it's green for you and it's always green, that's all good. But if it's normally brown and it turns green all of a sudden, you're like, I ate what I normally eat, be mindful of it. Occasionally stool turn really dark and black. That's sometimes a sign that there's blood, and especially if it's black, it's old blood versus red being fresh blood. Sometimes turning black is a sign that there's been an overdose of something like iron. So sometimes over consuming certain nutrients will change the color. Some of you like to drink beet juice. That'll turn it red, right? And so, or eat a lot of beets. Something to be concerned about? No, but it's good to know that if it turns red, it's not from any other reason that you had too many beets. So color is a matter, as is smell, actually, that we're getting to next, matter of consistency and change. If the smell, again, it shouldn't smell like roses. However, it should not clear out an entire like campus, right? If you go, or your entire dorm room, wherever you live. And so the smell should have some consistency. Again, like color, it's associated with what you eat. People who eat a lot of meat has a tendency to go rancid in our body and produce much stronger smell. So people who eat meat-based diets are going to typically have a lot more pungent sort of smelling poops than people who are on plant-based. Plant-based people have typically a lot more gas, but less smelly gas. So again, a change in the smell, if there's no change in diet, can be a red flag. All of a sudden it smells really strong. Nothing's changed. Perhaps there's lack of absorption of something going on. There could be lack of certain enzymes. There's, again, multiple potential sources of these changes, but mostly just be mindful of the changes. Technique. And this is, yes, how should you be going? I want you to Google Poopin' 2.0 Underground Wellness. This is a Sean video. It's 7 minutes long. There'll be some test questions on it, I promise. But technique matters, right? And Sean talks about in the Poopin' 2.0 video about how anatomically we aren't, when we sit on the sort of what he calls the modern toilet, when we sit on the toilet, we're not anatomically in a good position. And that affects, or it can affect the stress that we put on our digestive tract when we go, and can lead to issues, things like a blowout of our ileocecal valve and other things. So get to watch the Poopin' 2.0 video. It's only 7 minutes. So ultimately, and the bottom line is, yeah, you need to have a look, right? In my face-to-face classes, that's your homework assignment. Yeah, go poop, and you need to be ready to tell us about it. We'll have that discussion. Clearly, in an online class, I'm not going to do that to you, but have a look. Evaluate it. Yeah, print out that Bristol stool chart. Put it in your bathroom. You don't have to do that. So finally, taking care of your GI tract, it's important. It's a big deal. We barely scratched the surface on how important it is. And what the consequences of not doing it are in this discussion. We just don't have time to get that deep. But ways to take care of it, stress is probably one of the closest or one of the strongest influences on GI health. If you can find ways to relax, not just throughout the day, but throughout the day, but also when you eat, right? And you guys have a mindful eating assignment in this class. That's one of the purposes of that assignment, to really make you mindful of this is the way to eat to make sure we maximize the potential of our GI function. Other things are kind of healthy lifestyle stuff. Avoid toxins, basically avoid crappy food and take care of your body. Make sure that you're regular, meaning that you go on a regular basis. That might mean drinking more water. That might be eating more fiber, whatever it is that's slowing your digestion down. Improve it. Eating well, exercising, chewing your food well. Those are all ways to improve and take care and lessen the stress on your GI tract. You could probably think of some other ones. So, all right, we're done with digestion. Going to jump into metabolism next. Thanks for your attention. Enjoy the beautiful Australian beach. Until next time.